Push that rock with Simpson Math. We're going to study polynomials this next week. And in this video, what I want to do is kind of remind you that you already know a lot about polynomials. Constant functions that are always the same number, like going through, this is supposed to be going through b here, y equals b, or y equals 5, y equals -2. They're flat lines. Those are 0-degree polynomials. Lines in y equals mx plus b are first-degree polynomials. Which one of these has a negative slope? Can you tell me that? You should be able to tell me. This one has a slope m that's less than 0. This one has a slope that's greater than 0. Quadratics, parabolas, are second-degree polynomials. See, the highest power on the exponent is 2. That's where we get the second degree from. But they're second-degree polynomials, and you know a lot about quadratics. You know they look like this. If a is positive, then they open up. Notice they have, and this one has, they don't always have, but this one has 2 x-intercepts. We call those roots, root 1 and root 2. They open down if the leading coefficient is negative. We call this the leading coefficient, and that's the degree. Here's the linear term and the constant term. Some vocabulary for you. Now, the interesting thing about parabolas, actually quite fascinating thing, is the types of roots they can have. So here we have a second-degree polynomial, but it really only has one root. It has a root at 2. If you factor it, you get x minus 2 times x minus 2. If I put 2 in, this goes to 0. But that's the only number that's going to make it go to 0. So it's a distinct root. We're going to say that it has a multiplicity of 2, or is a double root. And mathematicians are weirdly going to count it as 2 roots. And the reason why they're going to do that, it's weird, there's only one there, but they're going to count it as 2 because there's 2 factors that could give us that root. See, that doesn't happen on a line. If I graph the line y equals x minus 2, well, 2 makes that 0. And that's the only factor that I could put and then we go up 1 over 1, up 1 over 1, so the line looks like this. That's the only factor that will take that root in. So that's just the regular cross the x-axis. Notice here, we didn't cross the x-axis. Something kind of weird and special happened because we had a double root. That's interesting. Another typical quadratic is one like this, where it factors, and we see the root is clearly 3. So 1, 2, 3 is a root, and then -2 is a root. Because if I put in -2 plus 2, that's 0. 0 times anything is 0. So it's when they're factored, it's really easy to see the root. That's a big deal. So if you can factor the thing, and when we study polynomials, we're going to be all about trying to factor it, because if we can factor it, we know where the roots are, and that really helps. Sometimes it doesn't factor, and we'd have to get these roots from the quadratic formula. And these roots aren't rational numbers, they're irrational numbers. That's interesting. Another thing that happens is it just doesn't have any roots. So here's a parabola whose vertex is up here and it goes up, so it never crosses the x-axis. It has roots in a technical sense. You might say they're not real. And in fact, every polynomial of degree 2 has 2 roots. Wait, we just said back here there was one with a 1. Oh yeah, but we count it as 2. So we say every polynomial of degree 2 has 2 roots, but they're not necessarily distinct, and they're not necessarily real. So when it comes to graphing, that knowing that every second degree polynomial has 2 roots doesn't help us a lot, because it might just be 1, and it might not be any. So, but it's a fact, okay? Now, we investigated these enough, and we used this formula enough that we've come to realize that this thing under the radical really helps us a lot. In fact, it's called the discriminant. If this discriminant, b squared minus 4ac, is 0, well, there's just going to be the one root. Well, it's a double root, but the one root that's a double root. If this discriminant is positive, well, then there's going to be 2 roots, okay? They might not be rational, though. The only way they're rational is if the discriminant is a perfect square. So if the discriminant turns out to be something like 4 or 25 or 100, well, then they're going to be rational roots. But if it comes out to be something like 17, well, they're going to be irrational roots. And finally, we could have a situation where the discriminant is negative, and then there will be no roots. Now, what you're going to be doing this next week is taking this knowledge and extending it to larger degree polynomials. Math made simple, some math.